Hello everyone, my name is Max Stilz. I'm from the University of Stuttgart, and I am recently working on chirality effects in pantographic structures, specifically pantographic cylinders. And I did this work, it's mainly split in three parts, so there's some beam simulations to show the effects based on a code that was mainly developed by colleagues from Stuttgart, Jonas Harsch and Simon Eugster. There were some experiments performed based on these simulations that were done in Warsaw. And then there is an approach to a continuum description of these cylinders, which I'm currently still working on. Okay, so chirality effects in pantographic structures are already known to exist. Just to remind you what a pantographic structure looks like, if you have forgotten or you've never seen one, which I highly doubt. We have the pantographic sheet, which is a layer of beams that are two layers of beams, and these layers are connected by something called a pivot. So what this connection may look like is it might be different. So it might be some kind of third beam, or it might be even something like a perfect joint, a rotational joint, or an actual pivot joint. So because of this structure, this offset between these two layers, these sheets possess a kind of handedness. So they are chiral in a sense, even though the structure itself is not chiral, but the sheet becomes handed. So as has been already shown by Dr. and colleagues, that there are chirality effects in extension of pantographic sheets. And this was a full 3D model, and also a continuum model has been developed which can replicate this behavior. Okay, to think about a pantographic cylinder, we have to think about this pantographic sheet just wrapped on a cylindrical surface. And in this case, the beams, they become helix. So just to remind you, a helix has handedness. A helix is already the prototypical chiral structure we know from our DNA and such. And so a helix has a handedness depending on if the beams are rotating, or the fiber or whatever is rotating counterclockwise or clockwise around the main axis. It has a radius, a pitch, which is just the height per revolution, and then you can define a number of pitches, and also get the length of the fiber per pitch. In Cartesian coordinates, then the parametric description looks something like this. We have this parameter S, which just goes from 0 to the length of the helix. And of course we can also describe it very easily in cylindrical coordinates. Then the pentacylindrical structure is simply helixes, which are the one layer is clockwise and the other is counterclockwise. So they also need an offset, so their radius has to be different, and then we can just use a number of equidistant coils, and then we get a structure like this. So for now they're just unconnected helix, and if we want to describe those as beams, we can, with the Frenet-Serre formulas, we can easily describe a tangent and a cross-section orientation. So if we want to describe them as beams, we have to define some kind of cross-section. Then, most importantly, we introduce a connection between those two layers, so the pivot. And also in this case of these pantocylindrical structures, this pivot always sits where these two beams are on the same radial and height coordinate. And yeah, you can see here these small dots. This is where this connection exists. And to simplify it in our simulations, we did not introduce these pivots as beams themselves. We used either no constraint at all, just for comparison. How does a spring compare to these pantocylindrical structures? We used a rigid connection, so we completely linked these two in all their degrees of freedom. Or we use a perfect pivot joint so that they can freely rotate around the radial axis, but all the other degrees of freedom are still linked. The code we used, as I told before, is mainly developed by Jonas Hart and Simon Eugster. It's a non-linear rod finite element code, so it's real beams, it's real rods, it's not solid elements. It's an in-house finite element code based on Petkov-Galerkin-Kossara rod formulation. It has an R12 interpolation, so 3 positional, and 3 times 3 cross-section unknowns. Of course, there are constraints coming to these cross-sections, but this is so far the most stable and most simple solution. The cross-sectional unknowns are parameterized by quaternions to avoid any problems like gimbal locks or anything. And the initial configuration, so we first have a straight configuration and then we use a non-linear square problem to fit each beam to a helix. And then the analysis of these results was as follows. We used a cylinder structure like I've shown before. We clamped this at the bottom and at the maximum height. And we perform compression tests, extension, shear, and some torsion tests. The parameters were, we used a single pitch, then we use a cylinder that is higher than wide, and we used 10 beams per layer, so in total 20 beams. The measure for chirality was when you think about this is a cross-section, so this is the y-x plane, so this is a cross-section of the cylinder, and if you compress the cylinder, you expect the cylinder to increase in its radius, but not only this, what also will happen is that there's a shift of the pivots or the beams themselves in one of these directions, and this breaks the symmetry and introduces a chiral behavior. So there's a preferred direction of rotation. And so I would call this in the angular displacement delta theta. I also looked at the pivot rotation angle, but this is a completely correlated measure of chirality. So it's enough to look at these shifts. So the compression tests, then they look like this. We compressed by about 1/3 of the original height. So you can see here from 0 to 1, this is just the total reference height. We look at the outer and inner beams, so the dashed lines is the inner and the solid lines is the outer beams, and we changed the distance between the two layers. So for completely uncorrelated springs, so this is a system of springs, there is no pivot, we see how a spring would behave in this experiment, and we can see that this for the inner and outer beams is completely mirrored. The inner beams is just we changed the distance, so this is why there is a small change here, but otherwise they're completely mirrored, so this is they're chiral. If we then connect these two layers by a rotational joint, we can see that in this delta theta measure, the outer beams, they dominate the system, so the shift will happen to the side of the handedness of the outer beams. And the dotted line you can barely see because the dotted line, they completely follow the solid line in this case. For the rigid connections, there is a buckling, which was expected because the structure is very, very stiff. But we can still see a handedness also in this case, but yeah, it is diluted by buckling. In the extension test, we see something very similar. Again, the springs have a mirrored behavior. In the revolute case and also in the rigid case, we can see this kind of S-shaped behavior. Here there's even maybe a double S-shaped behavior, but a chiral is very obvious. Then in addition, we perform some shear tests. The shear tests, they break the rotational symmetry, so you have to know what you're looking at, which pivots you're looking at. So we looked at the pivots that are here in front, so that are at this place, that are the direction they're shifted in. And then there is delta theta only in one direction, so there's also another complete break of symmetry. And then also torsion tests. The torsion tests also show a quite interesting behavior. The top three images here, these are all counterclockwise torsions, so in the direction of the outer beams. And we can also see a buckling behavior in these cases. They might look different, so this definitely needs a stability analysis. So where does this happen? How does it happen? But for the clockwise torsion, we don't see any buckling at all. It was kept completely stiff. So you can see that in the internal energy, that for these three ones, they get on a lower energy level, so this is a little bit higher than the other two, and for the clockwise torsion there is very high stiffness, so the energy still increases and increases. So this is a logarithmic plot. So the difference between those three is just some small numerical differences. I think I changed the element numbers or something, but as I said, there is a stability analysis needed. Yeah. So the experiments were performed in Warsaw. They used specimens printed from polyamide. They had near perfect pivot. We cannot really judge how perfect they were. That's still to be seen. But also elastic pivots used very similar parameters to the simulations. So far, we have compression and tension test results. And they used some DIC analysis of the vertical pivots position to show this chirality. And the results agree with what we see in simulations. We see these S shapes, so we see a clear chiral behavior. The only problem we have in experiments was it was very difficult to keep the clamped boundary conditions, as this polyamide, they easily slipped. So you can see that this is a little bit shifted from the initial clamped position, but the S shape is still obvious. For the continuum approach that I'm following, I just wanted to remind that there is a very straightforward general way you can approach this, which I really enjoyed following. And just with the toolbox of differential geometry, I have a generic set of curvilinear coordinates and have a reference configuration and a current configuration, capital and small x. And from this I can define the natural local basis, capital G and small g, and then the deformation gradient just tells me how this capital G transforms into the small g. So if I follow this approach and take a cylindrical surface and embed it in R3, I can very easily find my bases. They're not normalized. They don't need to be. So I easily find my basis vectors, and based on these, so I have my basis and I have my my curvilinear coordinates theta and y. And from this, so the angle, this is the angle in here and the height. And from this I can use an approach that has been used many times. I can embed in these cylindrical surface, I can embed Coursera rods, and I'm a triad for the counterclockwise L and the clockwise rods M, their tangent and a normal and a binormal. And then with the deformation gradient I have just defined, I can find also these triads in the current configuration, together with the stretch of the fiber. So, and from this current configuration, I can also, from the reference and current configuration, I can derive curvatures. So here it's important to note that here, of course, the fibers are already curved in the reference configuration. So I have to define a curvature in the reference and in the current configuration to find an energy density. And if I also want to, if the pivots are elastic and are perfect, I can also, of course, define the pivot, the torsion angle, so the angle between the fibers that gives me a twist of this pivot. And then I get a total energy density that is in the framework of second gradient elasticity. I have an energy density that depends on the first and on the second gradient of the displacement with respect to the curvilinear coordinates I chose. And then I propose some energy that is quadratic in these measures. So I have extension, and I have the 2 times 3 curvatures, and then possibly I also have the torsion of the pivot. But you may notice that this model does not involve any chirality yet, so there is no offset involved in any kind so far. But there are ideas. So as has been done before for the pantographic sheet, you could just define 2 plates for each beam and then couple these 2 plates by some constraint or even a first gradient continuum. Otherwise, you could also directly describe a 3D continuum and not a 2D one, and apply some stiffness gradient maybe along this radial direction of the pivots. Stiffness of the beam, so that there's 100% of the inner beams at the inner radius and 100 of the outer ones, and decreasing stiffnesses along the radius. Maybe it's also possible to still describe it as a 2D continuum, as some kind of projection on a 2D surface. I'm not really sure about that, if that can capture all the effects. But what should be possible is that if I only introduce different stiffness coefficients for the inner and outer beams, I already introduce a kind of chirality, but it's probably not the same behavior as through the offset. But it would also be interesting to follow up on that and see how this relates to the offset. Okay, so in conclusion, the chirality effects of pantographic cylinders, they could be shown for beam simulations and also for experiments to have this S shape. The influence of the pivots was mainly just observable for the beam simulations. They were not so much present in the experiments yet. But maybe because the difference between the elastic and the perfect pivots is not so big. The continuum model is still under construction, but basically everything is there. I just need to assemble it. Maybe there could be a new approach to the chirality than before, but there's already a viable method to follow. And yeah, what is still open is the choice of a framework for this second gradient continuum. Depending on which model I will use, I have to decide on discretization. If Alghero elements I can only use for 2D. If I want to do it 3D, I have to use Hermite polynomials, IGA, or maybe a mixed formulation. And then what follows then is an extended parameter study to quantify these chirality effects and maybe find some configurations that have even stronger, more prominent and interesting effects. I think this is only really viable if I have a continuum formulation. And then further, of course, a direct comparison between the beam experiments and continuum tests. Okay, thank you for your attention.